First, blunder repair. Last time, which is the first time I've done this, and I hope the last, I forgot to turn on the microphone for the video taping of our lecture on Monday. So if you look at the posted video, you will have the pleasure of retreating to the early 1900s and watch a silent movie. So I went through this silent movie yesterday and I posted, which I think are explanatory comments to allow you to follow this if you so choose. What counts in the main are the comments which are in writing on the chalkboard, which probably you have. Now then, somebody left this device here. I hear it rattling. I don't want it to rattle. It also struck me with the conversation with a couple of you folks who were seeing me, I believe, Monday or yesterday during office time, I don't remember. That the question number 3, which I had on bonus quiz 1 about 100% to 2 significant figure maximum ionization extent for an HAC solution is impossible. See what happens when you don't pay attention to detail? I get bitten just like everybody else. I'm not immune. I forgot to apply this recipe. I've done a lot of calculations on acetic acid solution and recognize that it goes beyond 99% for the very dilute solutions of acetic acid which so far I've analyzed. Like 1 times 10 to the minus 7 molar acetic acid solution, where in order to calculate the hydronium ion concentration, you have to factor in Kw. But if you apply this recipe to acetic acid and its Ka value of 1.8 times 10 to the minus 7, you get 99.44%. That's it. So you can't get it to 100%. So I told the instructors yesterday for discussion class to collect your work, and if you did anything that has meaning with respect to question 3, you'll get some credit. I will not penalize my students for my blunders. So here is an additional question 3. This one I know can be dealt with in accord with the boundary conditions of the question. Change the acid to this stuff. The name of this stuff is hydrogen oxalate ion. I don't care about its name. What counts the most is its formula, and you'll see the formula for this in the acid-base table, of course, occupying a higher position than acetic acid because it's got a bigger Ka value. So do the calculation for this solution. You can turn it in next Tuesday as your passport to take quiz 2 in class quiz 2, which as the syllabus tells you is next Tuesday. All right? Now then, at long last, let's finish chapter 18. Which I have chosen to labor on in detail because it underlies understanding so much of what we have yet to do, particularly chapter 19. We'll complete this by wrestling with this. principal acid-base equilibrium is this. Has a very small K value. By way of what you've been doing in discussion class the last couple of weeks, you've learned now about calculation of equilibrium constants. Values for equilibrium constants, which are for equilibrium reactions for which the K value is not given. Complex equilibria, I call them. Complex in the sense that the equilibrium whose K value you are to determine is an equilibrium which is composed of two or more fundamental equilibria. What are the fundamental equilibria at which we have so far become familiar, or for which? Ka's, Kb's, Kw, and at the onset of chapter 19, KSP. So at this stage of the game, any K value you have to evaluate will be composed of two or more of these equilibrium constants to which we have just referred. And at the tail end of chapter 19, we'll introduce you to yet another equilibrium constant, which bears the label K sub F, where F means formation. Formation of a complex ion. More on that when we get there. In any case, what I just said underlies evaluation of K for this reaction, which happens to be Ka ammonium ion over Ka hydrogen sulfate ion. Now back to the problem at hand. How do we get the hydronium ion concentration for this solution? Well, first of all, we should recognize that the principal species, which of course comes from PSI, ammonium ion and sulfate ion, and if we're going to do a calculation, we've got to have quantitative principal species inventory. So let's first look at the quantitative species inventory from a molarity standpoint rather than from a moles standpoint, since we're going to do a concentration calculation. Ammonium ion concentration is 1.0 times 10 to the minus 5. Sulfate ion concentration initially is 5.0 times 10 to the minus 6. With this K value, do you think this reaction will serve to diminish the ammonium ion molarity as well as the sulfate ion molarity appreciably? This a big number? Oh no, that's a very small number. So the extent of this reaction is very small at best. So we're not going to observe any particular degree of diminishing of the initial molarities of ammonium ion and sulfate ion by this equilibrium. Now then, before we do the analysis in detail, what kind of hydronium ion concentration max can we expect for this solution coming from ammonium ion? Well, we can apply x squared over m sub I minus x to the reaction ammonium ion plus water, double arrows, hydronium ion, ammonia, specifically Ka ammonium ion. That's what I did here. And get 7.5 times 10 to the minus 8. Now I put a question mark after 7.5 times 10 to the minus 8, which I'll explain in a moment, but at the minimum, if this is truly a handle on hydronium ion concentration max that comes from ammonium ion, does this tell us that we have to consider Kw to calculate this hydronium ion value, hydronium ion concentration value correctly? Yes. Is this not an acidic solution? Because Ka ammonium ion is a lot bigger than Kb sulfate ion. Ka ammonium ion is small, 5.6 times 10 to the minus 10, but Kb sulfate ion is only 8.3 times 10 to the minus 13. As we've already noted, sulfate ion's ability to behave as a base by reacting with water is pretty doggone small, practically speaking negligible. That'll come up again in later conversation.
Where did you get the 1.0 times 10 to the negative 5?
That's the concentration of ammonium ion in this solution. All right. In any case, back to this value. At the minimum, this value is less than 1.0 times 10 to the minus 7, and we know this is an acidic solution. It cannot possibly have a hydronium ion concentration which is smaller than 1.0 times 10 to the minus 7. That's impossible. So this value, if nothing else, is screaming at us. You've got to consider Kw. Now, what about this being hydronium ion concentration max? Nope. We'll go back to that part of the puzzle which yours truly messed up regarding bonus quiz 1, question 3, as originally stated. The maximum ionization extent of ammonium ion by reaction with water. Because this reaction, even though it's larger extent than the reaction of ammonium ion with water, this reaction does not make hydronium ion nor hydroxide ion. So as we recognize in getting a handle on the hydronium ion concentration for a solution like sodium bicarbonate, you got to look at a reaction which makes hydronium ion or hydroxide ion. So we look at ammonium ion plus water, hydronium ion ammonia products, which corresponds to Ka ammonium ion, and we apply our max ionization extent based on dilution. So here's Ka ammonium ion. Ka ammonium ion plus 1.0 times 10 to the minus 7. This hydronium ion concentration cannot be smaller than this in a very, very dilute solution. Gives 0.56%. That's a pretty tiny ionization extent. Not surprising, though, given that Ka for ammonium ion is such a small value. So now we'll take the initial molarity of ammonium ion and multiply it by its maximum ionization extent, which gives 5.6 times 10 to the minus 9. This is the true value for hydronium ion concentration max that comes from ammonium ion in this system. And it's a good deal smaller than 1.0 times 10 to the minus 7. Upshot, Kw has got to be part of this analysis. The hydronium ion concentration in this system depends on two species in the system: ammonium ion and water. Water reacting with water to establish the Kw equilibrium. So we also ask, because our PSI has showed us that sulfate ion is the principal solute base in this system, do you think we have to pay attention to this reaction? Well, this reaction corresponds to Kb sulfate ion. Kb sulfate ion is 8.3 times 10 to the minus 13. To what extent can sulfate ion, by reaction with water, affect pH? More to the point, generate hydroxide ion by this reaction. We'll take this recipe. Put in Kb sulfate, 8.3 times 10 to the minus 13, 8.3 times 10 to the minus 13, and you will get a value which is a hell of a lot smaller than this. It's only 0.004%. I think that's what I got for my arithmetic. No, 0.00084%. Who cares about that? So we can forget this. That's not going to have any effect on pH at all. All right? You think we need any other equations to solve this puzzle? What are these other equations? Tell me what they are and then we'll write them down. And material balance. MB first. There's MB for all material forms of ammoniumide. Or if you want to say all material forms of ammonia, who cares? MB for all material forms of sulfate ion. You think we can legitimately simplify this MB statement by canceling this? Hey, we already talked about the fact that you're not going to make any hydrogen sulfate ion in here that's going to be measurable. All right. Charge balance. I will, of course, write the charge balance statement on the board. You write it. Total moles positive must equal total moles negative for charge balance to exist. And all bulk chemical systems are charge balanced. You get this? Not difficult, really. Can we set this equal to a charge sum? If you're writing a complete charge balance statement, yes. And are we not trying to calculate the hydronium ion concentration? Is it that what we want to do? Are we wanting to calculate the hydronium ion concentration? Yeah. Then we better keep this in.
Yeah, but if you ignore for other situations,
what?
Would you ever use the non-complete charge balance equation?
Well, we use what we need to use to answer the question. You can't avoid answering the question. And this question is about calculation of hydronium ion concentration. So you better keep hydronium ion concentration in the charge balance expression, since that's what you want to calculate. Back to the question. Can we set this equal to a charge sum? What is that charge sum?
1 times 10 to the minus 5.
1.0, please. You folks throw away significant figures like they were rotten apple cores. Don't do that. Why is this legitimate? Have we not recognized that sulfate ion, practically speaking, isn't going anyplace? So this, we can write in for this. This, we've demonstrated, is in essence negligible. And does this introduce a new unknown? Hell no. This is this. So this charge balance equation winds up not being particularly difficult at all. All right? Now then, by this, do you realize we're bringing KW into the picture? How about that? So now, I'm going to write Ka ammonium ion, because that's our main acid in the system beside water. which of course is equal to this. You know, this is way back to the start of chapter 18. Now, do you believe with the expressions we have here that we can solve for ammonium ion as well as ammonia in terms of hydronium ion? Do you believe with what we have on the board we can rewrite Ka for ammonium ion so that it is an equilibrium constant expression which contains one and only one unknown? What do you think that unknown is going to be? The hydronium ion molarity, because that's what we want to calculate. You know, we can solve this thing so as to make it an expression in terms of what we want to find out. Now, my experience has told me that many of you folks need this fundamental algebra practice. So I'm going to write what this becomes after you do what I told you to do. Based on what we have on the board, we solve for the ammonia molarity in terms of hydronium ion as well as the ammonium ion molarity in terms of hydronium ion. Here's what you're going to get. Hydronium ion stays in. Ammonia becomes this. In the denominator, we'll have (1.0 times 10 to the minus 5). In terms of language, we have used many times previously. What's this correspond to? M sub I ammonium ion. And the equilibrium molarity of ammonium ion, which if nothing else follows from our mass balance expression, is (1.0 times 10 to the minus 5) less the concentration of what? Ammonia. Because when ammonium ion reacts with water, what does the ammonium ion convert to? Ammonium ion behaves as an acid, loses H+, and all of a sudden it's become ammonia. Now, have we got the value for ammonia on the board? Have we got the molarity for ammonia on the board in terms of hydronium ion? There it is. Okay? So if you can recognize by playing with these equations that the ammonia molarity in terms of hydronium ion is this, you've really done the algebra, and it's not difficult. You do it.
For finding the concentration of ammonia, not ammonium ion, and just ammonia, couldn't you also use the charge balance?
We are using the charge balance.
Okay.
Yeah. Okay, so here I'm going to continue with this. And there it is. One equation, one unknown. Now my bet is that many of you, when you solve this, you won't write hydronium ion here, you'll write X. Don't do that. Keep it as hydronium ion. So you wear out a little bit more ink or pencil lead. Who gives a damn? You're trying to learn. If your main goal in life is to be a conservative with respect to graphite consumption, so be it. But if that's your main concern in life, I don't know why the hell you're here. I can assure you that where you're going to wind up, if this is your main concern in life, is probably standing on a street corner with a cup like this that's got a bunch of these graphite containing things standing in there and offering them for sale. Pencils. I told you, I didn't explain it, other than to tell you, it comes from algebraic treatment of these expressions. You do it. You sit down and do it. It's not difficult. I know this is where you folks in the main need practice. I don't know how the hell algebra is being taught in our schools these days. But I see so many of you folks absolutely mystified by the simplest of algebraic expressions. And I know it's not your fault. I know you've been mistaught. I don't know why. And I haven't been in the class with you, so I don't know what the heck was offered. But I surely am convinced that what was offered was a bunch of baloney. Mixed up junk. That's got to go away. And you are the forgers of the future. If any of you go away from this gathering after it's completed and say, maybe that SOB Horvath had something on the ball and we ought to carry this forth because we do want people to learn, then maybe you'll do something about it. I hope you will. I can assure you, for as long as blood flows through these veins, that's exactly what I'm going to do. That's why I was so excited to be able to get this class of mine on the internet. If I have my way, I'm going to have the great blessing and privilege of being able to teach this stuff to every student like yourself in the whole world. The whole world, any place in the world, who wants to get a good strong handle on chemistry in his or her first year of university. Because I know for a fact that in most first-year university chemistry courses, and I'm sorry to say this, but my observations have told me that it's true, not much goes on of consequence. I hear the teachers of this wonderful stuff saying, oh, they'll get this up in upper-level courses. Ha! What if this is the only chemistry course they're taking? I don't get that cop-out. I want this course to be as meaningful as it possibly can be. And that's why I do what I do. And I can only hope that you folks who are really here with the intention of learning realize such. Enough sermon, let's proceed. Okay? You will find out for this solution, if you go through all of this, the hydronium ion concentration to two significant figures will be. Now before I write this down, I'm going to write the value down so you know what you're targeting, shooting at when you go through this. How do you think the value I'm now going to write down, the hydronium ion concentration for this solution, will compare to 1.0 times 10 to the minus 7? Now we know that the value will be 1.0 times 10 to the minus 7 or something bigger because we know the solution's acidic. But I expect a better comparison than that. What I'm asking you about is, do you think the not final, but the hydronium ion concentration for this solution will be pretty close to or a good deal larger than 1.0 times 10 to the minus 7? What do you think? Pretty close to. Hey, this is a damn dilute solution. And water is a weaker damn acid than ammonium ion, isn't it? What's the advantage that water has in this system when it comes with respect to hydronium ion production compared to ammonium ion? Concentration. The material advantage. It's concentration. This is 5.6 times 10 to minus 5.0 times 10 to the minus 6 moles of solute? Pah! This is practically pure water. The molarity of water is 55.5 moles to 3 sig figs. Here's the answer. The huge value of 1.3 times 10 to the minus 7. Wow, is this a strongly acidic solution? Ha ha ha. Okay? And so at long last, we proceed to chapter 19. Given that, you've already had a good deal, made a good deal of progress with chapter 19. Now then, let's sum up what you have so far done in chapter 19 of consequence. You've been introduced to a new type of equilibrium constant. Its label is K sub SP for solubility product. It corresponds to this solubility product. A material of limited solubility, an ionic compound of limited solubility in water, dissociating into its component ions. And the solubility product constant is depending on the solubility of this material itself. Like silver chloride, double arrows, silver ion and chloride ion. Calcium carbonate, double arrows, calcium ion and carbonate ion. But for the two specific equilibria I just mentioned, there's a hell of a big difference in the chemistry of these systems. What is that big difference? For silver chloride dissociating in silver ion and chloride ion, we have the liberty of calculating the solubility for silver chloride directly from its KSP value. No other equilibrium constant values need to be considered, or equilibrium reactions. Why is that true? You've been through this. Why is that true, what I just said? Why can I successfully calculate, correctly calculate the solubility for silver chloride directly from its KSP? Don't have to pay attention to any other equilibrium reactions. Why is that true? I want to know if you've understood what you've so far done in chapter 19.
Because silver chloride is the only source of chloride or silver ions in the solution.
Your statement regarding the chemistry of silver chloride is correct, but your statement is not correct with respect to answering the question.
Because the two are equal.
Why are they equal, the molarities of silver ion and chloride ion?
Because silver chloride doesn't affect pH?
Silver ion and chloride ion don't affect pH. Remember, those are the ions that are in solution after silver chloride dissolves. Don't start writing anything like AgClAq, because I'm going to get out the biggest red pen I can get and I'm going to slash that stuff and take off 1 million damn points. When you start writing formulas for stuffs which ain't real, I get unhappy. Now that's interesting, because silver chloride, which we're going to talk about in far greater extent when we get to chapter 23, we've got to wait that far, is extensively molecular in character. And studies on silver chloride saturated solution show that there is AgClAq in that stuff. Molecular silver chloride, not silver ion and chloride ion. But we're not going to wrestle with that, because studies also show that when silver chloride dissolves in water, mainly you wind up with a silver ion chloride ion system. I mean, chemistry is rich and complicated. And for general chemistry to be taught as if, oh my, this stuff is so damn simple, everybody zips through and make A's, well, not learning a damn thing. Hey, I want you to all make A's, but I guarantee you're not going to zip through it and do that. You're going to have to work. And in doing this work, you're going to learn. That's what I want. Then you get an A that means something. Then you get an A that provides foundation for jumping into analytical chemistry class and organic chemistry class and later on the physical chemistry class and doing one hell of a good job. And then, like other students, with good fortune, you'll come back to me and say, you were a rotten son of a bitch in that general chemistry class. But boy, I learned a lot and I had a good time in organic class and I zipped through that, so I guess you're really okay. Hey, this has happened to me a lot of times. I like it. You got to be thick-skinned to some extent to do this. If all I did was pay attention to the complaining students, I would have squirreled my tail between my legs a long time ago and ran away. Oh, people are unhappy. I can't. And I said, nuts to that. You're here to learn. And if you don't want to learn, you're in the wrong place if you're in the same room with me. Now then, calcium carbonate, as we have recognized. In fact, we did a demonstration on this the first day of class. Now, most of you were here the first day of class, because only a few folks added the class after the first day. I took some calcium carbonate, saturated it in water, and added some phenolphthalein and saw the development of a red-pink color. Remember that? Yeah. I hold you responsible for every damn thing we've done in this class since day one. Period. That's the way life is. That's the way chemistry is. You have to keep in mind all the stuff that we've already done, because it lays foundation for what we are presently doing and what we shall do in the future. It's like learning math. Same thing. You want to go to calculus class and then at that point say, can I now forget all the algebra I learned? Well, you can. Well, what kind of grade do you think you can make in calculus class? How about a nice 0? That's a good score. Carbonate ion, a base which is categorically weak but appreciably stronger than water, has a measurable ability to affect pH, which is why that deionized water saturated with calcium carbonate treated with phenolphthalein turned red-pink, giving to one significant figure a solution of pH 10.0. Well, hell, the solvent's got a pH of 7.0. So calcium carbonate on dissolving did more than dissociate. One or more of the ions put into solution, calcium ion, carbonate ion, affected pH, and we know it's carbonate ion. So now the system is more complicated from an analytic standpoint, because if you're going to get at the solubility of a material like calcium carbonate, beside KSP, you have to consider KB carbonate ion. You can't escape from it if you want to do it right. So with that, you have so far seen, and I hope understood, how you can calculate the solubility of calcium carbonate in deionized water by paying attention to, as simultaneous independent equations, KSP calcium carbonate and KB carbonate ion. You wind up with 2 equations and 2 unknowns. You can solve that. The solution's in the notes. Okay? Now then, with that, where S means solubility. Okay? You did in discussion class so far, consider S for calcium carbonate buffered at this pH. So, the first chemistry consideration you should pay attention to when you see this information is, how does S for calcium carbonate in this water solution buffered at pH 8.00? How does S for calcium carbonate in this solution compare to S for calcium carbonate in straight water? So I'll write down in parentheses CT for compared to, S CaCO3 in DIW for deionized water. Pure water, okay? Now, to get a handle on this, you have to go back to what we mentioned just a moment ago about the fact that when you saturate deionized water with calcium carbonate, you get a solution that shows a pH of 10.0, accounting for why the phenolphthalein became the red-pink color. And now you can answer the question. How does S for calcium carbonate in this system compare the solubility for calcium carbonate in deionized water, which shows a pH of 10.0 and has an S equal to 1.4 times 10 to the minus 4 moles per liter, which is a data point that's given in the notes. That's the solubility for calcium carbonate in straight water, determined by experiment and measurement. Without doing any calculation, you can now answer the question from a comparison standpoint. How does the solubility of calcium carbonate in this solution buffered at pH 8 compared to this number? Which is smaller? Which is smaller, S in the pH 8.00 buffer or 1.0 times 10 to the minus 4? Which is the smaller number? Let's say S or 1.4 times 10 to the minus 4. Which is smaller? Wrong. Flatly wrong. What have you been doing in the discussion class? This damn solution is 100 times more acidic than that. Isn't it? 100 times more acidic. And if you want to make calcium carbonate dissolve effectively, which you did in 2045L, remember doing that 2045L? In the solutions experiment, you took advantage of what you presumably learned from assignment 5 in 45L and took some calcium carbonate and treated it with some hydrochloric acid solution. And saw bubbles and fizzing, Alka-Seltzer reaction, and the calcium carbonate readily dissolving. Because if you want to get calcium carbonate to go into solution readily, with water being the solvent, you have to murder carbonate ion. And how do you murder bases? You hit them with acids, and that solution is 100 times more acidic. So that solution got to attack carbonate ion more effectively, which guarantees S in that solution has got to be greater 1.4 times 10 to the minus 4. And that's the chemistry. That's what you got to think about before you start doing any damn arithmetic. That's where it's at. Now I know this is tough and difficult. Just because I get all excited and jump up and down and holler, don't take that as I'm mad at you. I'm not. But I think this stuff is damned important. I think chemistry and water solvent is the most important chemistry in this world and will be forever so long as we things called humans are on this earth. Because we live in a water solvent life system. Maybe you go to some other planet, the way distant future, will you have benzene in your veins. Then you can do chemistry in benzene. But not now and not here. You got that? Question? We are next going to analyze the solubility of calcium carbonate in a water solution buffered at pH 6. How will the solubility at pH 6 compare to the solubility at pH 8? More soluble? Yeah. You're damn right, because now we're making the system ever more acidic. We'll pick it up from this point next time.